Let's start. Okay, so we continue with the tutorials today with Clément Mouhot, and he's going to talk about phase mixing estimates in kinetic theory. Please, Clément.
Okay, thanks, Jose. So I didn't know what angle to take here. So in the end, I'm going to spend quite a bit of time going at the basics of what I would call a phase mixing estimate and what it means geometrically, the connection with dispersion estimates. And in the second hour, I will mention one open problem in this first lecture, and I'll try to mention a brief review of results on damping in plasma and fluids and galaxies. We don't have much in galaxies in the second class, together with what I think are the most important areas or open problems to look at. I mean, there are many open problems because it's just starting. So let me start with a basic question, which is what is phase mixing? So part of this lecture will be often looking elementary, but I think it's good to have a good intuition about it. So in kinetic theory, a key word here is phase. It's not just a standard mixing. So in kinetic theory, we want to look at, of course, distribution on the phase space, position, velocity, as you all know, and this kinetic variable is what gives the name to the theory. So that's for the first word, phase. Now, for the word mixing, in dynamical systems, so the branch is essentially the mathematical abstract version of Newtonian mechanics. So it formalizes all this Hamiltonian dynamics. This field has several notions of mixing. So I want to warn those of you who would know a lot of dynamical systems. The notion of phase mixing we shall use is weaker than most notions. Stronger in general than the one we use. So I'm going to try to explain what is the notion we use. Example, a very important notion of mixing is, and totally different from what we use in kinetic theory, so far at least, even if, well, there might be connections soon in, for instance, in the recent work of Renato Velozzo, but in general, it's quite disjoint from what we do with phase mixing. Example, if you take the hyperbolic space or in general, something with a good negative curvature everywhere. And the geodesic flow is, I mean, it has no definition, but I want to insist on that, is violently mixing. But it's mixing in space. And of course, it's a very important property used a lot in dynamical systems and geometry. Here, the flow will not be mixing in space, but in phase space only. So here, typically, we have a second order dynamics on a flat space. Okay, that's not always true. For instance, for Einstein-Vlasov, we would have curved space. And in some instance, the hyperbolic aspect could pop up again. But in general, we don't expect to have such a gift as negative curvature. So we have something second order of that form. And on something roughly flat. So there's no intrinsic mixing here. And phase mixing, before we start writing equation, would mean in this context. So if you know about it already, this will sound trivial. If you don't, it will sound a bit cryptic initially, but we'll explain it. It means that particles following integral curves of this problem, particle close and on different energy levels. By energy levels, I mean anything that would be corresponding to the invariance of the dynamics. So it's in a generalized sense. So you take particles close by and on different energy levels, then they tend to get separated a long time. Okay, so it has strong connection with two things, and I will try to convince you of this conceptual connection. Strong connection with first the non-degeneracy condition in the KAM theory. For those of you who do dynamical systems, the KAM theory is to say that you understand sort of well perturbation of completely integrable systems. A completely integrable system is a dynamical system where you have enough invariance of the dynamics to essentially reduce it to a product of oscillators. I mean, that's exactly what it means. And the invariant tori, or the sets on which you have quasi-periodic orbits, because you have used all your invariants to reduce things to just a product of oscillations. And to apply the KAM theorem, which tells you that when you perturb that with a smooth perturbation, smooth enough perturbation, then most of the phase space is still covered with invariant tori. You need a condition which is a non-degeneracy condition, which is similar to what we're going to see now, which is to say that the way particle moves on nearby invariant tori tend to get them separated. And the second conceptual link is with the notion of anharmonicity in foundation of statistical mechanics, so in microscopic foundation of heat transfer. Okay, so let's take some examples to put a bit of equation into this. Of course, I'm going to take very, very stupid examples. So example one, we're going to take position in a flat torus. Okay, so you imagine your torus like that. You identify things this way. And you look at the dynamics, the most stupid dynamics you could imagine, with no force. Maybe stop that. Sorry. Yeah. So no force here. Yeah. And of course, the trajectories are straight lines. So you see, you would go there, then you would continue up here, and so on. So the physical energy is just a kinetic energy. It is conserved, of course, where V is your x dot. But in fact, for this very simple dynamics, even V itself is conserved. The velocity itself. Okay, so in that case, this phase mixing occurs because there is non-degeneracy. The non-degeneracy here is so trivial that it's even hard to state. It's because when you change you change from one invariant state from one V to another V, two particles nearby with two nearby different velocities, they will get torn apart, they will get separated precisely because they have different velocities. So it's even hard to think of it because it's too much built into the notations. This particle are close by, and after some time, they will get separated because they just happen to have different amplitude. It would work as well with different directions. Now in PDE form, this starts getting a little bit more interesting and less trivial to write. So if you write the Liouville equation for this dynamical system, you obtain the free transport equation that we've seen a lot last week and yesterday. And so the typical kinetic distribution. And the equation corresponding to that would be this PDE. The reasoning still okay with a slightly more general transport equation, as long as you have gradient of B, which is a matrix now, non-degenerate. I mean, if it's partially degenerate, you could still do things, but to keep things simple, you could do partial things. Let's keep it at that level. Example 2. This is the one I think that is much easier to visualize, but this is not really the one that is necessarily the easiest to use. It's too idealized. Is when you simply have be like that. You have a center, and then you have rotations around the center. Okay, they're supposed to be all concentrical nicely, but okay. And you have certain angular speed, which I will materialize by these arrows. So here, the equations are a radius, which for some reason, for those of you used to dynamical system, you can already start calling A for action variable. A radius that doesn't move, you don't change your distance to the center, and some angle that moves according to a certain angular speed depending on the radius. And you obtain at the PDE level, obviously, the very simple following PDE. Theta is one-dimensional, so let's just write it this way, where now your distribution depends on TR and theta. And your energy levels now corresponds to constant radius, constant distance to the center, and the non-degeneracy is corresponds to grade B, which in this context is just B prime of R, to be non-degenerate. So, so observe that, for instance, if B is just R, so you grow the speed linearly with the distance, it's perfect. So that's a typical example you want to have in mind. And so what would happen here? It's very easy to visualize. Let me take a color. If you'd have a certain supported distribution of particles like this, then after some time, it will get like this. Because this part moves faster than this part. And after a longer time, if you wait several rounds around the stuff, you will get something even more complicated. It's not so easy to draw, but you will get something like that spiral again around. I'm not sure it's clear, but you probably get the idea. Something like that spirals like that, because the outer part of the distribution tends to rotate faster. And this is what it means by getting separated, you know? There is a certain shearing, cisaillement, I forgot the word in English, mechanisms that happens between different radius. Imagine horses on a horse racetrack. If they have different speeds like that, after a while, you expect to see your horses spread about evenly in terms of the angle variable. That's a discrete example. So at the discrete level, it doesn't fit exactly what we're going to do, because at the discrete level, you still have Poincaré recurrence mechanisms, but you don't have these recurrence things at the continuous level. Okay, so yeah, I meant, so the two connections, two conceptual connections I mentioned. First, link with KAM non-degeneracy. Well, it's very easy if you're familiar with dynamical system. It's just that if dynamics writes in action angle variable which is what you would expect from a completely integrable system, if it writes like action variable not changing along the dynamics and angle variable, now not necessarily 1D, you could imagine that they are each of them d-dimensional, and the angle variable changing by, which now this guy can be a vector, changing according to an angular speed depending on the action variable, then the non-degeneracy condition is exactly a multi-D version of what we did before. Okay, so the link is completely immediate. Now the link with anharmonicity is okay, slightly less direct. However, I believe it's very much connected. Okay, so anharmonicity is used for a lot of things in mathematical physics and statistical mechanics. So yeah, okay, we could have polemics about the term, but let me explain what I mean here. Consider the Newton dynamics in a confining potential. I'm going to take something as simple as I can in order to have easy intuition of things. Into confining potential that we'll call whatever, small phi in 1D. By 1D, I mean my position is in R, my velocity is in R. Okay, so then what it means is that the integral curves, let me keep the track of the time variable, are just this, or the characteristic curves, if you want, or just this. And so it's in 1D, it's just a dx. Sorry. And this depends on the position. So if we try to visualize things, it's quite easy. Of course, I'm writing something extremely easy. In such low dimension, your system is always completely integrable. So that's why I went to low dimension. So I don't want to have discussions about other invariants. Okay, I won't manage. Yeah, not so bad. So let me take as well that phi my potential is 0 as 0, and phi is increasing. Then the energy is kinetic plus potential, and it is conserved along the characteristics, along the trajectories. So each energy level determines a certain curve. Okay, it's not necessarily a perfect circle, but okay, I only have circle recognition. So you can imagine it's something else depending on the shape of phi. So it's an energy equal constant curve. So on this trapped curves, so that would correspond in practice to trapped regions of phase space. For instance, if you have matter orbiting a star or a black hole or something, you will have a region that would somehow correspond to that in higher dimension. Then, in this context, the harmonic oscillator, or the harmonic potential, I should say, sorry, which is phi of x is equal to x2 over 2, x squared over 2, corresponds to, interestingly, the worst case from the viewpoint of phase mixing. It corresponds to, so let me go back to my equations. It corresponds to x dot is equal to v, and v dot is equal to minus x. So, of course, we solve that explicitly. Your curve will just be x0 and v0 will be my initial data. Let me try to write it correctly. Like that. Okay, so you have explicitly the curves, and now in that case, they are exactly circles as in my drawing. So the problem here is that the angular speed is the same for all circles. In other words, if you have a distribution of particles here, after some time, they will get exactly here, exactly here, exactly here. They will just move around, rotating without any change of shape, any deformation, any dispersion. In other words, let's just call that perfect, what is called, yeah. I wanted to say a manège. So in English, it's a perfect merry-go-round, which is the extreme opposite to phase mixing, is the worst case scenario. So phase mixing or non-degenerating CAM condition, if you want, requires or is similar, let's put it this way, to anharmonicity, which interestingly corresponds to nonlinearity of the force of the gradient of the potential. So that's, by the way, a very nice feature of foundation of statistical mechanics, that probably the oldest law of physics expressed with differential relations, the Fourier law. Well, I don't know if it's before Newton. Anyway, one of the oldest requires anharmonicity, which means non-linearity. So it's a linear law, the Fourier law, but it is really relying upon some level of non-linearity at a microscopic level. So the Fourier law is, as you know, the fact that there's a gradient proportional to the difference of temperature linearly. Okay, so Yeah. So to summarize these two examples, and these two connection links, I will now formulate the main idea of phase mixing in kinetic theory at a very broad level, and then we'll try to write some estimates to make it more clear. Is under the ideas that under suitable non-degeneracy conditions, if needed, which is completely trivial for free transport, but far from trivial as soon as you will have more interesting geometric features like a magnetic field, or you're in a curved space-time, for instance, matter orbiting a star or a Schwarzschild or Kerr black hole. It will become really non-trivial at all to satisfy these sort of things, to check these sort of things. Under some suitable non-degeneracy conditions, can we use this weak, it's a weak form of dispersion, of mixing, to stabilize nonlinear PDs? Well, of course, we won't be able to stabilize all the time, obviously, in some cases, at least near certain stable states, and with lots of regularity, as we shall see. Okay, so before the next thing I'm going to do is to start doing estimates on the transport equation, but I want to just make a remark, because I'm using phase mixing just because it's a very nice term that has been popularized in astrophysics and galactic dynamics by physicists, but also correspond to something I think very accurate at a dynamical system level. However, for those of you who would be more into plasma physics, I think it's important to know the sort of translation. So phase mixing used in galactic dynamics. So if you want to see a classic, nice pictures and discussion, a classical reference is the book by Binet and Tremen. But essentially the same mechanism is known as filamentation in plasma physics. And it's visible. It's visible actually with the aurora, CF. So the northern and southern lights. So you can see filamentation in the way solar winds, which is a form of plasma, enter the atmospheres in the aurora borealis or australis. I mean, you'll find plenty of pictures on Google. So this is one, but it's not the only manifestation of filamentation, of course, but this one is visible and beautiful. So it's usually called filamentations in plasma physics. I sort of knew, but I forgot. I mean, in the context of two-dimensional fluid mechanics, Euler, I don't know if there's a third terminology. If Jacob is around, he would be the expert. No, he's not around. Anyway, I guess it's also called phase mixing for 2D Euler, but if I remember the other name, I'll come back to that. Okay, so now back to the transport equation. So now what I'm going to do is I will try to convince you that phase mixing estimates are not unrelated to more traditional dispersive estimates. So they are not sort of complete outside what's been done before in PDEs. They are certainly very much related, but they are not exactly the same. So I will present various estimates, dispersion, averaging lemma, and phase mixing, and how they are connected for the transport equation. I made this remark before. A small remark. Note that because I mentioned dynamical system, note that the estimates that will follow are only true at the continuum level. What I mean by that, we're not allowing particle trajectories like Dirac mass to the transport equation. Because if you do allow Dirac masses solution to your transport equation, you're actually going back to point Newtonian mechanics. And if you do that, you're going back to ordinary differential equations. And you can't prove things like asymptotic for all times because you will have recurrence phenomenon. Even if the recurrence time could be crazy, mathematically you can't avoid it. Okay, so the toy model we're going to work with is, of course, the one you've seen. We're going to work with the transport operator. And remember that it's more universal than it looks like. So remember that it could be considered as a sort of slightly simpler model for a general action angle variable evolution. Okay, so that's not a bad idea to start to try to understand that toy model first in details. So one word first about the characteristic method. So we'll need the conservation later. So since it is simple, and I'm sure most, if not all of you, have seen a proof at some point or another, I'm just recalling things without the calculations. Imagine we're trying to, I'm stating it in a slightly more general form in case we need it. Imagine we're looking at such transport equation. So you have a force here, you have a certain transport term here. The characteristics are given So this is capital X is the position characteristics starting at little x, little v. And you solve things like that. It's a bit tedious to write, but I'm sure you've seen that before. And if you write your characteristics, let's say, we'll suppose that F is, for instance, C1 and F has a growth condition. So with that, you have global characteristics with these conditions. And then the solution is defined implicitly. You could, of course, invert the characteristic map to be more specific, but I won't need that for the moment, so let's leave it. And I will use this F in always in the talk for my initial condition. Okay, so this define the solution. To check that, you can just differentiate that equation in time, and you will check that it gives you back that. And the version of the Liouville theorem here that is useful for us is that if we define G of xv to be the determinant of derivative of capital X, so the derivative is in little x, little v. I hope it's clear. And derivative of capital V in little x, little v. So each of them you see as D rows, 2D columns. So you put the two of them together, you create something square. You can take the determinant nicely, and this object evolves like so. The divergence of the force in V at the new velocities times G itself, times J, sorry. Okay, so as a conclusion, the important thing I wanted to highlight in the Liouville theorem is that J is not zero. Observe that J at 0 is always 1. And J is always 1, stays 1 for all time if your force is depending on X. Okay, so that's the volume conservation in phase space, and therefore then you will have that your solution conserves all your LP norm. Okay, here you could put RD in X, or you could put the torus. I will tell you when it matters. For the moment, let's keep RD. So V here. Okay. So by the way, it's not just the LP norm, it's anything. You would also have that the Boltzmann entropy that has been talked about in the previous lectures is conserved, etc. You could take any functions of F itself. So all these things conserved are called the Casimir functionals. Importantly, for the transport equation we are looking at, the characteristics are very easy to write, and we can invert them immediately, and we just get these explicit solutions, of course. So let's start now with dispersion estimates. Well, not all of them, but an example of them. Good references on that were papers by Pertam, and one is with former student, I forgot the name, in the early 90s, but there are other papers using very similar estimates actually. So let me give you one example, extremely easy to prove. But and again, I'm going to detail dispersion, averaging lemma, and phase mixing so that you can see that they all come from the same underlying mechanism and how they differ slightly. Oh, thank you, Nicolas. Nicolas Bess, yeah, my question before that, so it would be called differential rotation in fluid mechanics. Okay, what I'm calling phase mixing here. Yeah, so the mechanism, maybe let's first try to picture the mechanism. The mechanism for a dispersion estimate here is that locally, we're going to try to prove things like a local, well, sort of local. It's not completely easy to pair it with the terminology in Schrödinger equations, but it's more or less a local dispersion estimate. And what we are going to say, we want to quantify the fact that particles, when you have a bunch of particles here, they will tend to disperse in a position because due to slightly different speeds. Different velocity. But to see that, to see the dispersion, you need to average in V. So let's see how it works. So the key estimate would be F at time t and infinity in X, L1 of L1 in V. Okay, so that means the order matters. That means you take L1 in V, then you take sup in X is less than T, so you can run it forward or backward in time. So that's why I'm putting the absolute value. It could be T positive or T negative. And then you'd have F0, F of 0, L1 of X, L infinity of V. And this is for all T in R except at 0, of course. So that's the estimate. And how do we prove this? Well, it turns out to be pretty easy to prove. I mean, you would find it. You would find it in 2 minutes with a piece of paper, obviously. You just start from the left-hand side. This is a supremum over X, so in RD, but let me not repeat the domain each time, of, okay, integral in V, ftxv. Now, what I'm going to do is to use the explicit formulation by the characteristics, sup in X of integral in V, f initial X minus Vt V. Now, the key point is to take a supremum according to the second variable. Okay, if I take this function add V in the second variable, it's less than the sup in the second variable. So less than sup in X, integral in V, sup in something else that we shall call W of F initial, let me put an absolute value here, X minus Vt W. And now I'm doing a change of variable. So I'm going to call that V tilde, and I'm going to change variable. So I get less than sup in X of integral over V tilde, sup in omega, F initial of, oh sorry, V tilde is really an extremely bad name, so let me call it Y, of YW dy. And now you observe that this sup can be dropped, doesn't appear anymore, and that I've exactly written the F initial L1 in X of L infinity in V. Okay, so that's, oh, and forgot, of course, that was the whole point of this argument. When I do the change of variable, I get a T minus D here, which is here. Okay, so it's not always used in this super simple form. The article, I should have checked that, sorry for that. The article of Pertam and I forgot his name. Anyway, they prove something slightly more technical that looks much stronger, but that actually is deduced from it by Ristorin. You can deduce something more flexible. You can prove that FT now.
I think it was Castella.
Ah, Castella. Thank you, Jose. You can prove that this is so it's a very similar estimate where observe that the two Lebesgue again are swapped, and you prove that only for Q greater than P. And they're both allowed on top of this condition. They're both allowed in the whole range. So how do you prove this? It's essentially applying restoring until death. So you just say that so you have so the map, it's a linear map. Okay, you have a linear map that maps f initial to f at time t. So that's the map I will apply restoring on. And you have for this map that L infinity x L infinity v is mapped with bound to the same space with bound 1, obviously. Okay, this is because it's a transport equation, so the characteristics tell you this. And then I have L1x L infinity v, which is mapped into L infinity x L1v, and this one has t minus d. Well, let's take t positive to avoid writing the absolute value all the time. So if you restore and interpolate between the two, you get immediately that your map, so I restore and interpolate only at that space level and that space level, and you get that this is true with t minus d over p. Now, second step, you combine this with LPX, LPV mapped into LPX, LPV. So that's my Casimir functional. So the bound is 1 this time. Okay, and then if you combine the two, you apply again restoring. That's where I need that Q is above P, so that Q is interpolated between infinity and P. You get exactly LPX, LQV to LQX, LPV, and check it, you get exactly the minus D 1 over P minus 1 over Q. Okay, so maybe a small visualization of that. I want the role of the visualization is to convince you that it's actually the same mechanism than we use for phase mixing. It was just used differently in this previous work. Oops, I don't know what it is. Anyway, so the mechanism is could be pictured as follow. Imagine I start. Sorry, so that's that would be X, that would be V, and imagine I start. Imagine I start with a distribution of particles here. It's a bit arbitrary what I'm doing, but let's take it this way. So it is at time 0. Then how will it evolve? Well, at a later time, let me put another color. It will look like that. Okay, so that would be t equal whatever, 1. And at an even later time, okay, that one is not that correct. Okay, that's definitely bad. So that would be time 2, let's say. So you see what's happening. The speed is higher here, so the particle moves faster to the right. Now, if you average in the velocity variable, so that's what this vertical line is meant to represent. So you averaged along v, then you will immediately see why. It will immediately become clear why you get the style of estimates I wrote before. Right? Each time you average along v, you will get something smaller and smaller because it's been stretched. So there's less of the particles here. So you average along v, you get something smaller. So that's how your pointwise in x estimate of the average in v can get smaller along time. So this is again a manifestation of a particle in nearby energy levels of conserved quantity levels tend to get separated, to get torn apart. Okay, so now I think we still have time before the lunch break to present the averaging lemma. So averaging lemma, the origin this time is not Castells-Pertham, it's older. It was in the PhD of François Gols, and it's the most famous papers are Gols, Pertham, Santis, Lyons, and it was also in the partial version was in a book by a Russian mathematician, which is I think it's Agoshkov, if I remember the name correctly. About the same year than as the PhD of François Gols. So imagine you have the following transport equation with a source term S. And I give myself phi function of V bounded with compact support. By the way, there are tons of formulations of averaging lemma. My goal here is just for you, I hope in 5 or 10 minutes, you'll have a good intuition of what it is and how to use it or to reprove the versions you like. So an example would be the following. I'm going to look at the average in V of F. So it's not fully rigorous. I'm going to write the variable even if I'm going to take a norm, but I think it's clearer. So I'm averaging F against var phi, and now I'm taking a norm L2 in T, H1/2 in X. And that would be controlled by F L2 TXV plus source L2 TXV. So like I said, there are tons of variants. I really don't want to lose time on that. Of course, this one is hard to apply in a PD problem because you lack localization and so on. Okay, so you need to work more. But what is the idea behind that? How come you can get a bit of regularity out of seemingly nowhere? Because that's an hyperbolic PD. So you're not supposed to gain derivatives. The reason is the following, and it's connected again to the same underlying mechanism as phase mixing. The idea is that if you average transversally to to the what would be called to the singular set, well, singular set, to the cancellation set would be a better name, of the symbol of your hyperbolic operator then what would happen? And you will see the calculation, the 4 lines calculation I'm going to give you is exactly doing this. Well, if you have an hyperbolic operator, the reason it's hyperbolic rather than elliptic is precisely because the symbol has a set where it vanishes. In this case, you see exactly what it is. If you take Fourier, it's when the Fourier frequency in X is orthogonal to V, or if you have Fourier in T as well, tau, the Fourier of T, plus V dot Fourier of X would vanishes. So that's exactly what characterizes an hyperbolic operator. The fact that, well, it's not only that, you also want to be able to solve locally around Cauchy hypersurfaces, but let's stick to that. It's not elliptic precisely because the symbol has points of escape. There are points where you can, there are sets where you can oscillate, where you lose the ellipticity, the regularization. Well, what's going to happen here is that if you average in V, which happens to be always transversal to the lines along which the symbol vanishes, then by virtue of doing this average, the bad region where the symbol vanishes will be small because of the averaging, because the volume will be small in the average, and away from this bad region, you will still recover ellipticity. Still, so to finish that, it allows to retrieve a bit of ellipticity. So that is the idea behind that. So let's do that. Let's take Fourier. Fourier in T and X. Okay, so let me write it with a hat. I'll have Fourier with other variables later. So let's keep hat for this one. Okay, so I'm writing tau for the Fourier variable of T and Xi for the Fourier variable of X. And I'm integrating in T and X. Well, I don't pay too much attention to the normalization constant of the Fourier transform. Okay, so let's forget about that. And the equation in Fourier becomes obviously just simply tau plus V Xi multiplied by I, the complex I, times F hat is equal to S hat. So now let's do the estimate. I'm going to take 1 minute more, Jose, and then stop after this estimate. It's enough to look at Xi greater than 1 for the regularity. So, so either trust me or write it down if you have a piece of paper. I mean, it's harder for me to write all the details on the screen. Oh, sorry, what am I looking at? Yeah, because I mean, proving that with just L2 of T and X on the left-hand side is more or less trivial. So if you do that, you take care of the small frequencies in X, and what remains to be proved is only the not so small frequencies in X. So no loss of generality, we assume that. And then you look at your velocity average, but Fourier transformed in T and X, and you split it into an integral where the symbol of the hyperbolic operator is greater than some alpha, plus another part of the integral where the symbol is small. So that's exactly what I was describing before. Let me do a small picture. So if this is the space for V, if this represents, okay, I'm not good at centering circles visibly. Good, I'm not an artist. So that would be the support of my function varphi I use for the average. You remember varphi was compactly supported. And let's draw a line here, for instance. It's not necessarily passing by 0 because I have this tau. So that would be the line tau plus x v equals 0, the bad region, and I'm writing something around it with size alpha. That's what I'm doing. I'm cutting close to the bad region and away from the bad region. Okay, so should I stop here, Jose? Should I finish the calculation after lunch, you think, or should I finish just now this?
It's what do you think it's going to take? I mean, if it takes, yeah, I mean, it's up to you.
Okay, let me just write it down because it would be weird. Yeah, I'm going to take 2 more minutes. So we were just estimating that. So here I'm continuing there. So on the first one, I'm using that F is a solution. So here I'm just going to say greater than alpha, right? I don't repeat what is greater than alpha. I think it's clear that it's this. And then I multiply and divide by the symbol. So if I multiply and divide by the symbol, I make appear my source term, the right-hand side of my equation. And I have var phi divided by the symbol. And then for the second one, I keep it as it is. So it's the small light green region. And I have this like that. So now the remark is the following. The remark is that here, by doing Cauchy-Schwarz, I'll get S hat tau xi dot, and it will be L2 in V times something like that. One half. The second one, I'm doing Cauchy-Schwarz as well, and I get F hat tau xi dot L2 in V. And now I have integral on the small region of this 1/2. And just observe that, I'm going to write it down with the other colors. It's really an easy calculation. Just by using the compact support, using a small change of variable, only the component of xi along collinear to V matters. So that's only a dimension 1 decay you get. So that would be less than 1 over xi to the 1/2 with a constant, of course, and that would also be less than 1 over xi to the 1/2. So you deduce indeed that what I wrote initially, and I'm done, Jose, you deduce that your initial velocity average in V is less than something, a function that is this weight times a function that is L2 in tau and xi. This and that. Okay, and that's how you gain this regularity. The 1/2 is optimal in this example. What's not optimal is that I did not show any gain of regularity in time, but I don't want to make the proof more complicated than that. So I'll stop here to now do the phase mixing estimate after the lunch break.
Very good, Clément. I would then suggest that we postpone the questions for later, unless there is any question right now in the audience.
Yeah, that works for me.
I'm just waiting to see if somebody is. No, nobody reacts. Yes. Okay. Maria,
Well, I have a
fine.
question.
Okay, Mark, go ahead.
Oh yeah, does the last bound of the integral of phi in the region where it's smaller than alpha, how do you get it?
Yes, this one.
Yes.
It's yeah, it's literally looking at the volume of that thing.
Okay.
It's really just that. So look at that. Where is it? Look at this thing. What does it mean? You know, if the component of xi collinear to v becomes large,
Oh yeah.
you see you can scale by it. You can divide by it if you want, and that would give you a volume that becomes smaller and smaller proportionally to 1 over this collinear component of xi along v.
Okay.
That's nothing more than that. I'm just saying that when xi becomes large, this light green region becomes smaller and smaller.
Yes. Thank you.
Okay, so let's resume then 5 minutes after 1. Okay. 1.
Okay.
Okay. See you later.
Bye.